All right, welcome to section 3.11. We are looking at something called hyperbolic functions. All right. So to introduce this concept of hyperbolic functions, I want to go back a little bit all the way to trig and remind us of the trig functions. And trig functions are also sometimes called circular functions. They're also called circular functions because how they relate to each other is relative to a circle, right? This point here would be cosine theta, sine theta, something like that. All right, and then all of our other four trig functions can be built upon cosine and sine. And then because we have these nice relations, we have this fact, it's the equation of this unit circle, x squared plus y squared equals 1 becomes cosine squared equals 1. Okay, so now we're looking at something called hyperbolic functions. And if you remind yourselves what a hyperbola looks like, there's two different types of hyperbola. We'll do the horizontal version. Hyperbolic functions relate to the hyperbola. Okay, so for instance, if this is x and y, we know x squared minus y squared could be equal to 1 or something, right? That would be the equation of this, where this point is 1 and negative 1. All right, so hyperbolic function, that's a conic function. That's something we learned in our pre-calculus course. And our hyperbolic functions are going to have the same relationship. Instead of cosine, they're going to look like cosine with an h of x. And then instead of sine, it's going to be sine with an h, of x, for instance, where cos squared minus sine h squared is equal to 1. Okay, so this is what our hyperbolic functions are going to behave like. And while we're here, notice I'm using x as the argument. Before, when we were looking at cosine theta, sine theta up here, theta was the angle, right? In this case, on our hyperbolic function, again, that's just a quick little overview, the area, that hyperbolic sector, what we call that right here, this area, I'll use a darker pen, is x over 2. So the argument is twice that area. So that's how we're defining the argument of this hyperbolic function. All right, so that's visually what our hyperbolic function is. Where it stems from is we know e to the x is popular in calculus because we set up our derivative of the exponential function to just be itself. It's a function whose rate of change is proportional to the function, right? This is stuff we all remember about e to the x. And in all these calculations, they noticed they were looking at different combinations of e to the x. And it happened so often that they decided to just, figure out a definition for all of these even and odd combinations of e to the x functions. So this is how we're defining everything. So sine h, the hyperbolic sine function, is equal to e to the x minus e to the negative x divided by 2. The hyperbolic cosine is similar, but it's e to the x plus e to the negative x over 2. And then the other 4 functions are some combination of sine or cosine. So the hyperbolic tangent, just like in trig, it's the sine over cosine. So hyperbolic sine over the hyperbolic cosine. And then cosecant, hyperbolic cosecant is 1 over the hyperbolic sine. Hyperbolic secant, 1 over hyperbolic cosine. And finally, hyperbolic cotangent is 1 over tangent, hyperbolic tangent, but we can just write it still in terms of sine and cosine. Okay, so that's that. So let's look at some quick sketches of these hyperbolic functions. I'll just do sine, cosine, and tangent. We can sketch some kind of like asymptotes, some tendencies to help us with the sketch of the hyperbolic. So I'm first going to sketch the hyperbolic sine. And it's bounded by two functions, 1/2 e to the x, and then negative 1/2 e to the negative x. So that's fun. All right, and then our sine function just kind of comes and has a tendency towards these two. The end behavior, I should say, is going to tend towards those two boundary functions. So this one I just drew in blue, that's your hyperbolic sine. All right, and then visually we can see that it's an odd function. It has that symmetry about the origin. And the domain and range are both real numbers. All right, so moving on, let's look at hyperbolic cosine. And same thing as before, we have some boundary functions. And we're going to be looking at 2. Just as before, it's y equals 1/2 e to the x, and then y equals 1/2 e to the negative x. Let's see if I can draw that fairly accurately. And these are going to help determine the end behaviors of the cosecant or hyperbolic cosine. Okay, and let's see. The hyperbolic cosine is going to go through 1, and it's going to tend towards these curves as the end behavior. All right, so domain, if you can see, is all real numbers. It's an even function, also an even function. Even functions are symmetrical about the y-axis. And the range starts at 1, so it's going to go from 1 to infinity. Okay, you can also write it like y is greater than or equal to 1. Okay, and then I like this one too because you guys in Calc 2, in Chapter 7, you're going to start seeing more applications of these hyperbolic functions. And one application is the hyperbolic cosine models how a heavy wire hangs. Okay, so if you're, to suspend a wire on 2 points, the way it hangs from those 2 points can be modeled by the hyperbolic cosine. But you guys will see more of that in Chapter 7 in Calc 2. All right, and then finally, let's take a look at the hyperbolic tangent. And the boundaries here are just horizontal asymptotes at 1 and -1. And -1. All right, and then we come in and we have something like that. Okay, and we can see it's an odd function. You can see by that symmetry. The domain is all real numbers, and the range is stuck between that -1 to 1. Oops, excuse me. Not including. So we need a soft bracket. Okay, so there you go. So a nice little introduction to our hyperbolic functions. And then just like our trig functions, there's properties, identities, if you will. So a couple of things arise from the fact that they're even and odd functions. So if you remember, for odd functions, if you plug in a negative value, a negative x, you get back the negative y. And that's just a property of odd functions. Even functions, when you plug in a negative x, you get back the normal y. All right, so those first two properties are just the result in an odd and an even function. Because they're hyperbolic functions, we saw that the hyperbolic cosine squared minus the hyperbolic sine squared is equal to 1, because that's the equation of a hyperbola. All right, and then these are your main ones, just like we did in trig. And then we can derive others from these facts. For instance, if we came through here and divided everything by the hyperbolic cosine, we would get this. Okay. Actually, let me check on that one. And then same thing if we came in and divided everything by, right here, the hyperbolic sine. We would get this one. Okay. All right, and then also, in addition, we have some double angle formulas as well. So if we take the hyperbolic sine, and it's of x plus y, we can prove this in a similar way we did in trig, but we get kind of a similar formula for trig for the double angle. And then if we have the double angle for cosine, for the hyperbolic cosine, it's similar to the one in trig, but instead of doing the opposite sign, it's the same sign. Okay, so there you go. So let's prove one. And we'll prove the hyperbolic identity first, where we're saying cosine squared h x minus sine h. Oh, I messed that up. Lots of notation, right? There it is. Okay, equals 1, and we're going to prove it. Okay, so we're going to prove this, and how we work with these identities, we go back to the definition of what it means to be a hyperbolic cosine and the definition of hyperbolic sine. So, for instance, the definition of the hyperbolic cosine is e to the x plus e to the negative x over 2. That's what the hyperbolic cosine is. Then we're going to square it. And then the hyperbolic sine, we go back to the exponential definition. Okay, and we want to show, we're not allowed to show this part yet, but we want to show that this whole thing is equal to 1. Okay, so let's square these out. Okay, so we're going to, you know, a binomial squared is a squared plus 2ab plus b squared. So we're just going to go for that. So e to the x squared plus 2ab. So just squaring a binomial right now, plus e to the negative x squared. And then this is going to be over 4. And now we're going to subtract e to the x minus e to the negative x all squared. So same thing, e to the x squared minus 2ab plus e to the negative x squared all over 4. Okay, so let's clean everything up. This is going to be e to the 2x, right, our multiplication rules. Here, when we're multiplying the same base, we add up the exponents. X minus x is 0. E to the 0 is 1. So 2 times 1 is just 2. And this is going to be e to the negative 2x, okay? And then similar thing over yonder, e to the x. This is essentially, a number times its inverse is 1. That's another way of looking at it. All right, so let's see what we have. So luckily we have the same denominator. So we're going to get, well, we'll just throw in an extra step. Why not? Okay, so let's use parentheses. So we're subtracting the entire numerator, not just the first term. All right, and then look at e to the 2x minus e to the 2x. That's going to go away. That's going to cancel. Let's see, 2 minus negative 2 is 2 plus 2. That's 4. And then we have e to the negative 2x minus e to the negative 2x. That's going to cancel. Okay, and so we're left with just 4 over 4, which is 1. And that's exactly what we wanted to prove, right? We wanted to show that this is 1. So our proof is done. So we can do a little square with a box in it. All right, so now let's start talking about the derivatives of all of these hyperbolic functions. And to demonstrate our technique for the derivative, let's look and see how we would show that the derivative, how we would find the derivative of the hyperbolic sine, okay? And again, what we do is we go back to the definition of what it means to be a hyperbolic sine. And the definition in terms of the exponent is e to the x minus e to the negative x over 2. So we can take the derivative of this, just using all of our rules we have. So I don't have to use the quotient rule. I'm just going to pull that 1/2 out to the front. So dividing by 2 is like multiplying by 1/2. And so I'm just going to focus on taking the derivative of e to the x minus e to the negative x, okay? Okay, so according to our rules, we can worry about the constant at the end. The derivative of e to the x is e to the x. The derivative of e to the negative x is the derivative, that's a chain rule. So take the derivative of the outside function first. So just, e to the u, e to the negative x, times the derivative of the inside function. What's the derivative of negative x? Negative 1. Okay, so we have 1/2 e to the x minus becomes plus e to the negative x. Okay, and then we'll put this in a form that looks a little bit more familiar. This is like dividing by 2. What does that look like? That's the hyperbolic cosine. Okay, so there you go. And then you can also show, let's take the derivative of the hyperbolic cosine. Go ahead and push pause, see if you can do that, and then we'll see what we get. All right, so the key is to relate it back to the definition. And the definition of the hyperbolic cosine is e to the x plus e to the negative x over 2. And then if you take that derivative, let's see, the derivative of e to the x is e to the x. The derivative of this is going to be e to the negative x still. And then the derivative of negative x is negative 1. And that's exactly what the hyperbolic sine is. All right, so let's write some of these down. So we did the first 2. This is what we just showed. And notice it's really similar to the trig functions. One difference is that normally the derivative of cosine is negative sine, but in this case the derivative of the hyperbolic cosine is positive hyperbolic sine, so that's a little bit different. The derivative of the hyperbolic tangent is something similar to the circular functions, secant squared or hyperbolic secant. Okay, this is going to be negative hyperbolic cosecant, hyperbolic cotangent. Hyperbolic sine. Hyperbolic secant. Again, it's, similar, but sometimes the signs are different. And then last one. Okay. And there you go. So we know how to take our derivatives now. And a nice way to memorize, notice all of these ones are positive and then all of the inverses are negative. So that's kind of nice, okay? So now that we have these rules, we can apply all the other rules we know. We can use the hyperbolic functions in the quotient rule and the product rule and the chain rule, anything like that, because now we know all of their derivatives. Okay, so let's move on to the inverse hyperbolic functions. Okay, and then how we're going to figure out what the inverse functions are, we're going to use a couple facts. So let's consider the inverse hyperbolic function of x. All right, so we would write it like this. We know just how hyperbolic functions work, that this means that the normal hyperbolic sine of y is equal to x. All right, because that's how inverse functions work. If we have an ordered pair xy, then the inverse function becomes, yx. Okay, so that's what we're dealing with. And just to recall, remember that we just looked at the hyperbolic sine and cosine, and it dealt a lot with e to the x. Okay? What's the inverse of e to the x? Natural logs. So we're going to see that the inverse hyperbolic functions, instead of containing e to the x, we're going to have a lot of logarithms. Okay, so let's see what that looks like. So first up is inverse of hyperbolic sine of x is equal to the natural log of x plus the square root of x squared plus 1. And because the range is all real numbers of the hyperbolic sine, the domain is all real numbers in the inverse. Okay, and then for the inverse hyperbolic cosine, remember that the hyperbolic cosine is not 1-to-1. So we're going to look at, we're going to cut off here. Let's do a little. So this is a quick sketch of the hyperbolic cosine. So we're going to cut the graph in half. So x is greater than or equal to 0. And y is greater than or equal to 1. And we do this so it's 1-to-1. And then once a function is 1-to-1, it has an inverse. All right, so we have to limit the domain, just like we do with the circular inverse functions. Okay, so once we make that restriction, this is what the inverse hyperbolic cosine is. It's really similar. We have to be really careful in our calculations. Do you see the one difference compared to the hyperbolic sine inverse? It's just this right here. It's the only thing that's different. And then we switch this. X's become y's, so the new domain is x greater than or equal to 1. Inverse functions, the domain and the ranges flip. And finally, the inverse hyperbolic tangent is equal to the following: 1/2 natural log of 1 plus x over 1 minus x. All right, and remember the hyperbolic tangent, our range had some limitations, right? So our range was this. So that becomes, except strictly. So our range becomes our domain. That's how inverse functions work. All right, and then once we have these three, the other three hyperbolic functions are just the inverses of that. So if we have these three, we can easily figure out the other three. All right, so these seem a little crazy. So we're going to figure out how we're actually getting such a crazy function. We're going to prove the inverse hyperbolic sine. Okay, so we get to prove that the inverse hyperbolic sine is equal to this. All right, so how are we going to do it? Well, let's go back to our inverse hyperbolic sine function, and we'll say it's equal to y. Okay, so if this is the case, then x is equal to hyperbolic sine of y. Okay, that's just how our inverse functions work, right? xy becomes yx. All right, so once we know that, we know the formula for the hyperbolic sine. The argument now is y. Okay, so it's going to be e to the y minus e to the negative y over 2. Okay, and that equals x. So let's cut out the middleman. So x is equal to e to the y minus e to the negative y over 2, right? X equals this. So let's clean this up. Let's multiply both sides by 2. So we get 2x is equal to this. And then let's make this 0. So let's subtract 2x from both sides. And I'm going to put everything on the left because that's how I like it. Okay, so we're subtracting 2x. Okay, so we make one side 0. And then remember e to the negative y, let's do a little thought bubble, is really, something in the denominator. So I'm going to clear that denominator. So how could we clear the denominator? We can multiply everything by e to the y. And that'll make sure we don't have any variables in our denominator. Okay, so e to the y times e to the y plus y is 2y, minus 2x times e to the y, minus, and that's just going to become e to the y times its inverse is just 1. All right, so we multiplied everything by e to the y. Okay, so here's where we get a little tricky. We are going to focus on the e to the y's. And what this is acting, this little trinomial we have right now, is acting like a quadratic. All right, where e to the y is acting as the variable. This is like, I'll write it like this. E to the y squared minus 2x e to the y minus 1 equals 0. Okay, so these things that I have right here, I'll do it in pink. Going back to like algebra class, if you substitute in an x, we can clearly see it's a quadratic because now it would be x squared minus 2x minus 1. All right, so x squared minus a coefficient x minus 1. So how we solve quadratics is we can use the quadratic formula, but instead of x is equal to the quadratic formula, our variable is acting like e to the y. So we're going to use the quadratic formula on this, where the pink highlighted part is our variable, and all the stuff in yellow is the coefficients. Okay, so let's see. In our quadratics, we have ABC. I'll do blue. So this is A is 1, B is negative 2x, C is negative 1. All right. Quadratic time. So x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And a is 1. All right, and that's what e to the y is equal to. So let's clean it up. So this is going to be, let's see, 4x squared plus 4 divided by 2. We can take out a 4 because that's a perfect square. So factor out a 4 and take the square root. We're left with x squared plus 1 after we factor out a 4 all over 2. And then look, we have a 2 in all 3 terms. That means we can factor out a 2 and cancel it. All right, so that's like canceling out a 2 in all terms. So we're going to be left with x plus or minus the square root of x squared plus 1. Okay, so now we have, remember what we were doing? This is e to the y. So e to the y is equal to x plus or minus the square root of x squared plus 1. Okay, and then because it's 1 to 1, we're going to say that e to the y is equal to just x plus the square root of x squared plus 1. And then we're almost done, right? This is an intense little proof. Okay, so then we have e to the y is equal to this. And eventually, we want to get a formula for y. We want to get a formula for y. And why do we want to solve for y? Because y is equal to the inverse hyperbolic sine. So we're almost there. Okay, so how can we get this for y? Well, we can write this in a logarithmic notation, right? We can also take the log of both sides, if that helps too. I think that's the most straightforward way. Then we don't have to remind ourselves of the definition of how we convert from exponential to logarithm. Because natural log and e, essentially they cancel each other. It's not really what happens, but it's a nice way of thinking of it, a shortcut way of thinking of it. All right, and then we have what we want, because again, remember, y is the inverse hyperbolic sine of x, and this is what we are trying to show. Okay, so there you go. It's intense, right? But we're learning all about our hyperbolic sines. So now what's next is we're going to look at the derivatives of the inverse hyperbolic functions, and we'll do that in part 2 of our video.